Most of our daily actions require very little thought. When you pour a cup of coffee, you aren't calculating movements, you're executing a biological habit. In cognitive science, these tasks are classified as an exercise. An exercise is a task where you already possess a learned procedure, an algorithm that guarantees a result. Multiplying 4 by 5 isn't a problem, it is a simple memory retrieval. A true problem only exists when an organism has a goal but lacks a ready-made sequence of actions to achieve it. As this diagram shows, an obstacle prevents you from reaching your desired state, forcing cognitive action. When blocked, you might wander aimlessly. A more efficient approach is setting a subgoal, a secondary step providing the resources needed to clear the path. This block only becomes a problem if there is a felt need to overcome it. If you aren't motivated to reach the goal, the obstacle is just a piece of the background environment you choose to ignore. Real problem solving is the deliberate effort required to bridge a gap when your habits fail. It is the work of the mind when it genuinely does not know what to do next. To study how we cross these gaps, researchers developed a formal framework to visualize the boundaries of thought. They call this the problem space. Every challenge starts at the initial state, the starting conditions and constraints of your situation. The goal state is the imagined reality you want to achieve. The actions taken to move between these states are called operators, tools used to change your current situation. In the natural world, operators are often physical, like climbing a tree to reach fruit. But in modern tasks like mathematics or logic, operators are entirely mental representations of actions. The difficulty lies in selection. From a vast library of potential moves in our memory, we have to find the specific operators that will actually bridge the gap. While mapping the space from A to B is a simple visualization, understanding how the human mind chooses the right path has led to a century of competing theories. Early behaviorists like Thorndike and Watson viewed the mind as a black box. They didn't believe in internal thought or reasoning, instead focusing only on observable actions. In Thorndike's puzzle boxes, cats would randomly claw at the door until they hit a latch that opened it. Thorndike argued that problem-solving was trial-and-error behavior being shaped and strengthened by the reward of food. Clark Hull later expanded this into habit-family hierarchies. This was a system designed to explain complex choices as a ranking of automatic responses. In this model, a stimulus triggers several potential responses with varying habit strengths. These triggers link into a compound mechanism. One response creates a new stimulus, but this machine-like view had a flaw. If an organism didn't already have a response for a specific stimulus in its hierarchy, it remained stuck. It had no way to analyze the situation. Behaviorism successfully tracked actions, but its refusal to look inside the mind left it unable to explain how humans actually understand a problem. Gestalt psychology challenged the behaviorists by focusing on how we organize our experiences. They argued that we don't just react to individual stimuli, we perceive structural wholes. They utilized the principle of top-down processing, the idea that you can only understand the parts of a problem once you comprehend the entire structure of the situation. Consider this matchstick equation. Solving it with standard math rules fails. The structure creates a mental block. Max Wertheimer called this blind application reproductive thinking, using old solutions on new problems, even when they don't fit. The solution requires productive thinking, a moment of insight where you re-represent the entire visual structure. You stop seeing a math problem and start seeing a geometric arrangement that can be moved. Gestalt theory proved that understanding was a measurable cognitive event, but it still didn't explain the specific data processing that leads to that aha moment. The 1950s brought the cognitive revolution. With the arrival of the digital computer, researchers finally had a powerful metaphor for human thought. The brain was now seen as an information processing system. We encode data from the world, store it in memory, and manipulate it to reach our goals. George Polya identified the specific phases of this process, creating a sequence of cognitive steps that mirror computer algorithms. This wheel shows the iterative nature of problem solving. It begins with understanding the constraints, then planning a strategy. The second half involves doing, executing the plan, and checking the result. The dotted lines show this is rarely a straight path. Human thought is highly iterative. We frequently hit dead ends and loop back to redefine the problem based on what we've learned. The information processing model turned the invisible mind into a sequence of measurable computations, providing a blueprint for the mechanics of thought. While the computational model explained the software of the mind, researchers also needed to find the hardware, the physical brain structures that carry out these tasks. Cognitive neuropsychology maps mental functions to specific physical tissues. By studying how brain damage affects behavior, we can see exactly which areas are responsible for different types of processing. Damage to Broca's area causes a specific deficit in language production. Patients can understand meaning, but the operators for grammatical structure are broken, preventing them from assembling words into sentences. In Wernicke's aphasia, the opposite occurs. The grammatical operators work perfectly, but the ability to process semantic meaning is lost. The speech sounds like language, but conveys no information. These language-specific failures show that the brain uses specialized modules to handle different parts of a task. Problem-solving requires these disparate regions to fire in sequence, passing data across the network. By linking these functional failures to physical anatomy, neuroscience provides evidence that the abstract operators of the mind are tied to the brain's biological architecture. This hardware has a major limitation: working memory. We can only hold a very small amount of information in our active attention at once. If our working memory is so limited, how do we solve complex, real-world problems that involve thousands of variables? We use schemas. The schema is a framework of default assumptions stored in long-term memory. When you see a house, you don't analyze every detail. You instantly load your house schema to understand its structure. Schemas act as a cognitive shortcut. They allow us to bypass working memory limits by providing a pre-packaged understanding of a situation, letting us focus only on the details that are unusual or new. This connects back to the problem space. Expertise is the possession of thousands of these specialized schemas, allowing an expert to instantly recognize which operators will work in a given field. Problem solving is an iterative cycle of efficiency. We encounter a block, deploy schemas to analyze the situation, and through repeated practice, we build new frameworks that turn today's challenge into tomorrow's automated exercise.